So good afternoon, everyone. Sorry, I should have checked the load shedding schedule before starting. Yeah. Thank you very much for joining us this afternoon. Some of you might know me, but some might not. My name is Francesco Petruccione, and I'm at the moment the interim director of NITheCS, which is the National Institute for Theoretical and Computational Sciences. Yeah? And today we try a few experiments. First of all, because COVID is hopefully behind us, we want to move all our colloquia every Monday at 4 p.m. To a hybrid mode, so that in case the speaker is in Stellenbosch or surroundings, we want to meet here. If the speaker is in New Orleans, maybe not. Yeah. And the second experiment is that we never hosted an event in a cinema. So we don't know exactly whether that is a good idea or whether that is a very bad idea. But feedback from the younger people here was that it was a good idea, but maybe you can let me know later. Yeah. So, but today you're not here to listen to me. You want to listen to Professor Tommie Meyer. He's the research chair in artificial intelligence at UCT. He's also director of our Center for Artificial Intelligence Research. Yeah. And he's, I think, still the only A-rated computer scientist in the country. No. Oh, okay. So maybe at some stage. The other two are in Stellenbosch. Okay. Sorry, Stellenbosch colleagues. I'm relatively new here and I don't know everybody. Yeah, so I apologize profusely. Yeah. But anyway, we are very happy, Tommie, that you made a long way from Cape Town to here. And we are very curious to listen to what you are going to tell us about knowledge representations, which is something that we read about every day in the newspapers, but probably not in a very professional way. So, Tommie, please, over to you.
Okay, thank you, Francesco. Thank you for inviting me. Let's see, is this better? Yeah. Okay, so as you can see, the title of my talk is Knowledge Representation in the Age of Machine Learning. Chances are that you've heard of machine learning. I'm not necessarily sure that you've heard of knowledge representation before, so I'll try to enlighten you today. But you'll see when I start with my talk, what I'm going to do before I start talking about CAIR, knowledge representation, in a bit more detail. I want to place this in the larger context of artificial intelligence. So I'm going to start talking about AI, much more general, and then towards the end of the talk, really, I'm going to focus on knowledge representation and how it links up to machine learning. And with that in mind, let me start with what may seem like an over-enthusiastic version of what AI is about. If you had not seen this type of headline in the newspapers in the past 5 to 10 years, I would say, then you're probably not reading newspapers or looking at the media at all. There's been a lot of talk about AI in general. So here's Elon Musk saying, I think we should be very careful about AI. If I were to guess what our biggest existential threat is, it's probably that. So we need to be very careful with AI, artificial intelligence. We are summoning the demons. Here's something similar by Bill Gates. A couple of years ago already. I'm in the camp that is concerned about superintelligence. I agree with Elon Musk and some others on this, and I don't understand why some people are not concerned about it. So the question is, what should we do when these alarming statements are being made about what is really, or to a large extent, an academic discipline? Now, the starting point is probably to listen to the expert, right? I think in many circumstances, at least, you can think of certainly Bill Gates and maybe even Elon Musk as being an expert in something. Here, for example, is Bill Gates in 2015 doing a TED talk, and you will see the little coronavirus there. He was talking about the possibility of a coronavirus pandemic hitting the globe at some point. My point being that, this is someone who's relatively good at making predictions. On the other hand, which expert should we be listening to? Here's Elon Musk in 2020 saying, based on current trends, probably there will be close to 0 new cases in the US by the end of April, right? So maybe not such an accurate prediction. And here, just to round this out, is Rodney Brooks, who used to be the director of the AI lab at MIT, talking about AI and saying nothing could be further from the truth. The AI being an existential threat. Almost all innovations in robotics and AI take far, far longer to be really widely deployed than people in the field and outside the field imagine. So in other words, what we have here is a bunch of experts. They disagree on whether this is a major issue or not. Now, at least to some extent in the talk today, I'm going to give you my opinion on this. I'll talk about machine learning and knowledge representation more specifically in a couple of minutes. But before I give you my sense of this, my idea, I want to make what I'm referring to as the Newcomb disclaimer. So Simon Newcomb was a Scottish mathematician. And he, in October 1903, made the following statement: "May not our mechanicians be ultimately forced to admit that aerial flight is one of the great class of problems with which man can never cope, and give up all attempts to grapple with it." So essentially, in 1903, October 1903, he was saying it's a bad idea to even try to invent flying machines because we will fail spectacularly. And pretty much 2 months later, we had the Wright brothers doing precisely that. So the Newcomb disclaimer is simply saying, you may be smart. Newcomb was certainly not a dummy. He was a well-respected mathematician at that point. The Newcomb disclaimer is simply saying you may be smart, but it is notoriously hard to make predictions about how things are going to pan out. So that's my disclaimer. I can tell you what I think, but with something such as AI, take what I say with a grain of salt, at least in terms of the predictions and, of where it's going. But in order to talk about that in more detail, then I want to start really at the beginning, and that is, what is AI? What do we mean when we talk about artificial intelligence? Now, there are almost as many definitions of artificial intelligence as there are artificial intelligence researchers. So I'm not going to start with a definition of what it is. What I'd rather do is give you a couple of examples. And I'm going to go back pretty far to the 18th century, where something was invented called the mechanical Turk, and this device was able to play chess quite intelligently. So what would happen, you see the picture of the device in front of you. It was possible for humans to play chess against this mechanical device. Now, it turns out that this was a bit of cheating, because in the little cupboard in front, there was a person sitting inside, and it was actually the person moving around levers and playing chess. Now, the question, in some sense, is whether this was intelligent chess playing or artificial intelligence. On the one hand, of course, it's not, because there was a person sitting inside. On the other hand, this guy must have been really good in order to be able to play a decent game of chess while sitting in there and manipulating these. So probably not a good definition of intelligence, I would guess. And then I'm going to move back, or to move forward quite far, right through to the 1960s. And I want to talk a little bit about automated therapy. Now, what you see in front of you is a computer screen, and it's really an instantiation of a little program called ELIZA. Now, this was developed by a guy named Joseph Wiesenbaum, who was at that stage, I think, the director of the MIT lab. I think he was the director of the electronic engineering lab, something like that. He developed a little system, which was very simple and relatively, well, it was a rule-based system. The idea was that it would be able to provide you with some kind of psychological therapy. As I say, the application itself was called ELIZA, so you would interact with ELIZA. Now, Wiesenbaum set this up to some extent, as history tells us, to indicate that something that's not intelligent can easily be viewed as intelligent. Nevertheless, even though he had this disclaimer, it turned out that quite a number of people really took this quite seriously and thought of this as a good therapist. Now, I know very little about psychology. Maybe this tells you more about psychology than about computer science and artificial intelligence, I'm not sure. But rumor has it that his secretary frequently interacted with ELIZA. So is this intelligence? Again, in some case, From some perspective, maybe it is. From a different perspective, maybe it isn't. Okay, then I want to jump from 1960 to the 1990s into the era where real intelligent chess playing became a reality. Now, since AI started as an academic discipline around the late 50s and the early 60s, one of the major goals was that the idea that a machine would be able to beat humans at chess play. In fact, there's a very nice quote by the famous AI researcher Douglas Hofstadter, who wrote the book Gödel Escher-Bach. Even in the early 70s, when he was asked whether he thought that machines would at any point in the future be better at humans than playing chess, his response was that he didn't think it was going to be that it's around the cards in the next 50 years or so, but that if it happened, it would only be if we had achieved a kind of general intelligence, artificial general intelligence. So it turns out that at least in that aspect, Hofstadter could not have been more wrong. Because what we had in the 1990s is IBM's Deep Blue, which was able to comprehensively beat the world chess champion, but doing so by having a very narrow version of intelligence, explicitly focused on chess playing. And again, the question comes up whether this is really or can be seen as intelligence. To a large extent, many people were quite disappointed in saying, yes, Deep Blue was able to beat the chess, the world champ, the human world champion. But this is not really what we envisaged when we talked about intelligence in the 50s and the 60s, in the same vein as the comment by Hofstadter. Okay, and then I want to jump to 2016, where we had a further extended version of very intelligent game playing. So again, my guess is that many of you would at least have seen or heard something about the Go world champion player and the fact that in 2016, Google's DeepMind developed the program called AlphaZero, which turned out to be better than, again, comprehensively beat the best Go champion in the world. Now, the reason Go is interesting, I don't know how many of you know the game, but it was long thought, well, firstly, it's realized, it's easy to see if you look at its complexity, that it's much more complex than a game such as chess. And even as late, I would say, as the late 2010s, feeling was still that it's going to be a very long time for machines are better at Go playing than humans are, because of the inherent complexity of the game. Never mind, despite that, in 2016, AlphaZero beat the current human champion at that point, and since then, machines haven't looked back. They've just become better and better in that. And then I want to jump to 2022 to ChatGPT. So again, my guess is that most of you at least would have heard about ChatGPT, which is really an intelligent virtual assistant. So what I did a day or two ago, I asked ChatGPT to write a paragraph explaining the place of knowledge representation in the age of machine learning. And here's what it told me. Now, if you look at this, you don't need to read this in detail. It's quite reasonable. It starts off by saying that knowledge representation plays a crucial role in the field of machine learning. Of course, immediately I like it, because my work is in knowledge representation. But the point being that, again, we have something interesting here. You look at this paragraph, it's well constructed. It certainly looks as if it's something that could have been constructed by a human. But there have been many cases in the past month or so where people have shown versions or paragraphs or even essays produced by ChatGPT, some of which really look fantastic. They look as if they're really coherent and intelligent, and some of them are just nonsense. So the question again is this intelligence? If you look at ChatGPT specifically, probably the best way to explain it, and I know this is an oversimplification, is that it's a souped-up version of autocorrect. But, if you look at it, it looks really intelligent. Okay, which then brings me to the question of, I've given you a couple of examples of what is certainly artificial intelligence. Does this mean that we are closer to machines being able to think? Can machines think? Well, Jerome Wiesner certainly thinks so. He's the special assistant to the US President for Science and Technology. And he said that I suspect that if we come back in 4 to 5 years, I'll say, sure, they really do think. A little bit later in the talk, I'll make some extra comments about this. But before I do that, let me then just talk a little bit more about what's the source of all the excitement. Now, I think most of you probably know what this is, and that is machine learning. Again, as I said at the beginning, most of you would have heard of machine learning, my guess would be, whereas many of you would not necessarily have heard of knowledge representation. So the current flavor of the month is certainly machine learning, and more specifically deep learning. Now, for those of you who don't know, the deep learning doesn't necessarily mean that we're talking about machines that can think deeply in some conceptual sense. It's about the levels in a neural network. So very broadly speaking, you can think of deep learning as a version of neural networks where you provide it with some inputs. There are weights associated with these, all these little nodes in the graph, and you get outputs on the other side. So in some very broad sense, it's a classification system. You put some stuff in, and on the other hand, it classifies it in some way or another. It's a cat or not a cat, and of course, more sophisticated versions than that as well. But this is certainly what all the rage is about at the moment, this form of learning. Now, here is my take on this, and I was certainly not the first one to come up with this particular way of looking at it. Many other AI researchers share this view, and that is the following. So the way in which it's articulated here is the way in which an AI researcher called Adnan Darwish put it. And what he basically says is that some tasks typically associated with perception or cognition can be approximated to a reasonable extent by fitting functions to data. And to a large extent, deep learning is fitting functions to data. The real point he's making over here, in my view, is that many of the things that we thought really just the exclusive domain of humans, in terms of really being able to think and understand, many of those tasks and many of these actions can really be done in a way that's not normally associated with intelligence and real thinking. It simulates it in some sense in a way, and then the question is whether this is real thinking or not. Okay, so that's my start, the start of my talk by just providing the context for AI and machine learning. And now I want to move into the area that's my area of expertise and the part that I'm interested in, and that is knowledge representation and reasoning. So here's, it's not necessarily a definition. Again, I'm not going to try and stick to a particular definition because, again, there are many various different definitions of CAIR, or knowledge representation and reasoning, but I think covers it relatively well. CAIR, or KRRs, sometimes it's referred to as KRR as well, is all about the following. It's finding appropriate ways of representing knowledge about some given domain of interest, whatever you're interested in. So finding ways to represent the knowledge appropriately. And then secondly, developing methods to derive implicit consequences from the information that you have explicitly given to you. Now, I'll give you an example in a second of what I mean by implicit information that you extract from explicitly represented information. But suffice it to say at the moment that the dominant approach in CAIR is logic-based. And not surprising because logic has a long history about formalizing reasoning and drawing conclusions and drawing consequences. Now, if you go to any CAIR conference, or if you go to any AI conference and you visit the CAIR section of the conference, you will certainly see logic-based work being done. You will also see other stuff as well that is not necessary or doesn't necessarily look like logic. But in virtually all of these cases, underneath what is being presented is a logic. There's a logic that formalizes it and that can take it further. So that's why I'm saying that in CAIR, the dominant approach is logic. Okay, so what do I mean by logic-based reasoning? So here's a very simple example. Suppose I am told that birds fly, that birds have wings, that birds have 4 toes, and that robins are birds. So I'm interested in the domain of birds for whatever reason, and I'm given this information. In many cases in CAIR, the assumption is that you know where the information, or you're assuming that there is a source of information. The question is how to represent it. Now I'm claiming, and I hope you agree with me, that if you look at potential consequences of the information that I've just given you, that the three ones that I have at the bottom there should certainly be viewed as consequences, right? Robins fly, robins have wings, and robins have 4 toes. And if you were to ask me why, the answer is, well, we know that birds have those properties. Birds fly, they have wings, and they have toes. And a robin is a type of bird. And therefore, those are birds of robins as well, because they're a type of bird. Now, this is hopefully, as I say, relatively easy to see. But of course, reasoning such as this can be much more complicated as well. And that's where the automating and the logic-based methods come in. So the formalization of logic has to do with being able to draw the correct type of conclusions under all circumstances. And in classical logic, it's fairly well understood. I want to take this a little bit further and show you what some of the consequences are if you make use of classical logic. So again, if I'm given the information that birds fly, that they have wings, that they have 4 toes, that robins are birds, but then I'm also told that penguins are birds and that penguins don't fly, then one of the conclusions that I can draw from this and that I should be able to draw from this is that there are no penguins. Okay, so why is that the case? So the argument is simple. On the one hand, I'm being told that penguins don't fly. But on the other hand, I know that a penguin is a type of a bird and that birds fly. So now I know that penguins fly and I know that they don't fly. And the only way in which this is logically possible is if there are no penguins. Now, this seems to be a little problematic because it seems to get us stuck into kind of an everyday situation that we want to be able to deal with. And a little bit later in the talk, I'm going to come back to how to resolve this type of problem. But let me just emphasize that from a classical reasoning perspective, the type of reasoning that you would do if you were constructing a mathematical proof, this is a perfectly reasonable conclusion to draw. Okay, so this type of reasoning, classical reasoning, can, at least in some cases, be done by making use of truth tables. So any computer scientist or engineer, and the disciplines close to computer science and engineering, my guess is that at some stage in your undergraduate career, you would have come across truth tables. My point is the following. There's a very simple way of performing the type of reasoning, in principle, simple way of performing the type of reasoning that I've just mentioned. And you can do this by what is referred to as SAT solving. And the SAT in SAT solving has to do with showing that something is satisfiable or consistent. Very simple example. Suppose that I want to prove that Q is an implicit consequence of knowing that P is the case and that if P, then Q is the case. So one way to do this, and again, if you had any kind of mathematics undergraduate course or even at school, you would have come across proof by contradiction. The proof by contradiction says, if I want to prove something, I take the opposite of what I want to prove, I add that to what I know, and then I see if I can come up with a contradiction. If I can come up with a contradiction, then the thing that I wanted to prove actually does hold. So in this case, if you look at the last column that I have there, if I know that P is the case, and I know that if P, then Q is the case, and I add to that not Q is the case, then it turns out that if you look at all the logical possibilities, those 3 statements together will always be false. So that means it's inconsistent, and from that we can conclude that P. So again, very simple example, but the point being that the only thing in some sense that we need to do here is we need to be able to show whether a number of these statements, and these are Boolean or propositional statements, whether they are satisfiable or not. And that you can do with truth tables in the simple case. Now, in the example that I gave you, there were 2 Boolean variables, right? P and Q. Boolean meaning that they're either true or false. That means there are 4 rows in your truth table, so you just need to check these 4 rows. In the bird example, there were 6 Boolean variables. That means there are 64 rows in your truth table. Now, again, you can deal with this, but it's a little bit more than just 4. And it turns out that in general, if you have n Boolean variables, then you have 2 to the power of n rows in your truth table to check, which is a lot. There's an exponential explosion, and then suddenly the problem becomes very hard. So in principle, SAT solving is intractable. In fact, officially, satisfiability is an NP complete problem for those of you who are interested in this kind of thing. But it turns out that modern SAT solvers can actually handle problems with hundreds of thousands of Boolean values. That doesn't mean that they can deal with all of these in the worst case, but many of these can actually be dealt with. So this is a reasonable way in which to perform the type of reasoning, or a reasonable way to implement the type of reasoning that I mentioned a little bit earlier. Okay, so that was just a very brief introduction about what I mean by reasoning and drawing conclusions from reasoning, and the fact that it can actually be implemented. There are tools that can help you to reason, to automate your reasoning process. Now, I want to go a little bit further and just talk, I think it's just 2 slides, about reasoning about knowledge. So again, this is also a version of reasoning, but it's taking it a little bit further. So in the previous example, we had statements about the world, and we were able to draw conclusions from that. Now I'm going to show you a very simple example of reasoning about the knowledge of others as well, and how that can help you to draw conclusions. So this is a classical problem in reasoning about knowledge called the muddy children problem. And what I have there, the picture on the slide is of 3 boys, 2 of whom have mud on their faces. The third one on the right doesn't have mud on his face. Now, the scenario that we have in front of us is of an adult that talks to the children and tells them, he makes an announcement, and he tells them at least one of you has mud on his face. And then he asks the children, do you know whether you have mud on your face? And we're assuming that the kids are perfect reasoners. What they're going to do under these circumstances is they all would have to say no. And the reason is any one of these kids look around, they see some other kids with mud on their faces. So if the only thing they know is that they're being told that there's at least one of them with mud on his face, there's no way for them to know whether they actually have mud on their faces. The assumption is that they can see the other 2 kids, but they can't see their own. So this is a perfectly reasonable statement of them that they would make. This is the only logical thing that they can do. But here's the interesting thing. If they all respond by saying no, and if the adult now asks them again, do you know whether you have mud on your face? Then after this, if they are perfect reasoners, the first 2, the one on the left and the one on the middle, in the middle, would say yes. And the third one would still say no. So why would the first 2 be able to say yes? Well, they could reason as follows. So let's take the first kid. He could argue as follows. He could say, suppose I didn't have mud on my face. If that was the case, then the middle kid would have seen 2 people or 2 kids without mud on their faces, and he would have been able to respond yes, but he didn't. And therefore, this must be the case. I must have mud on. Okay, so simple example. I hope you were able to follow my reasoning. The argument or the reason I'm mentioning this is that it is in principle kind of similar to the type of reasoning that I mentioned on the previous slides. In a slightly different way, it is a little bit different because over here we are now reasoning about the knowledge, the other information that agents or kids in this case have given us. So this is an area known as dynamic epistemic logic. And similar to the case, the SAT solving case that I mentioned, there are tools for being able to do this. In other words, there are languages in which you can express the fact that you're talking about the knowledge of others, and then you can reason about this. Okay, so that was my first example of extending classical logic or classical reasoning. And now I want to give you a second example. This is known as defeasible reasoning, and this brings me back to the penguins. So you may remember that I stopped talking about the fact that there are no penguins when we're given the information that I have on the slide up there, right? So just to recap, we know that birds fly, that they have wings, that they have 4 toes, that robins are birds, that penguins are birds, and that penguins don't fly. And then I said that from this, we should be able to, well, we are able to conclude that there are no penguins because we know at the same time, this tells us, all this information together tells us that penguins fly and they don't fly simultaneously, which is impossible. The only logical conclusion to draw from that is that there are no penguins. But if you think about this in a real world scenario, this is not what we want, firstly. And secondly, the reason we don't want this is something along the following lines. Frequently, when we make statements, such as birds fly, what we really mean is, well, birds usually fly. So we allow for exceptions. right? So there's the nice saying that every statement has an exception, right? Even this one. So the argument over here is that when we said birds fly, we actually meant birds usually fly, with possibly some exceptions, and that birds usually have wings and they usually have 4 toes. If you get to statement 4 and 5, probably that's more definitorial. So you would want to say that robins are birds and that penguins are birds. But then again, when we come to penguins, usually penguins not flying, what we probably mean is that they usually don't. So the idea of defeasible reasoning is to extend your language to be able to bring in this usually, this notion of usually, and then the question becomes, how does that affect your reason? So I want to give you 1 or 2 examples, and then I want to show you that feasible reasoning is not as clear-cut as classical reasoning is. The problem or the question of consequence and reasoning in the classical case is pretty much solved in principle. I think there's broad consensus about what it means to draw a conclusion. There are interesting questions to solve in terms of computation, how to make this more efficient, but we know what we mean when we talk about consequence. In the case of defeasible reasoning, it's not so straightforward. So I would go, I think, and I hope you would agree with me as a starting point, that when now that I've added these usually bits to some of these statements, we should be able to conclude, for example, that robins usually fly, that robins usually have wings, and that robins usually have 4 toes. That would not follow directly from the classical case because we've brought in the usually bit, but that seems to be reasonable, I think. If you don't agree, we can always talk about that a little later. But more interesting, I think, is the case about penguins, because in some sense, a penguin is an exceptional type of bird, right? So I want to ask the same type of question that I've asked about robins now, but now I want to ask this about penguins. Should we be able to conclude from the information that we have up there that penguins usually fly, that penguins usually have wings, and that penguins usually have 4 toes? And here is where, at least in some cases, as you'll see, opinions can diverge a little bit. So let me start with the first one. I think for any sensible form of defeasible reasoning, we should not be able to conclude that penguins usually fly. So the argument would be that because a penguin is a bit more specific than being a bird, if we have explicit information that says penguins usually don't fly, that should override the indirect information that penguins usually fly. So that seems reasonable. But what about the other 2? Penguins usually having wings and penguins usually having 4 toes. Now, it seems that, or it's definitely the case, that there are at least 2 arguments or 2 approaches to this. So the first one is usually referred to as presumptive reasoning. And presumptive reasoning says something of the following kind. It says that unless you explicitly know something to the contrary, then the conclusions that I have about the more general case of a bird in this case, should carry over. So, because birds usually have wings and penguins are birds, we should be able to conclude that penguins usually have wings as well, and similarly for penguins usually having 4 toes. There's nothing that says that they don't, right? And then the argument is, why throw away information? That's one argument. There's a second argument, and this is usually referred to as prototypical reasoning, that says, no, this is a bad idea. And the argument over here is that, and you can see this in the name of the type of reasoning as well, prototypical. The argument here is that, you know, a robin is a prototypical bird. It doesn't deviate from the standard properties of being a bird. So yes, it can inherit the properties of the general class. But we know that a penguin is exceptional. It can't fly. So then the argument is, why should we then immediately believe that it will have the other prototypical properties as well? So I'm not claiming that one of these is better than the others. I'm simply saying that these are 2 different approaches, 2 different types of reasoning. So this is a little bit different from the classical case because there seem to be at least 2 ways of thinking about drawing consequences or drawing conclusions here that seem perfectly reasonable. Okay, so defeasible reasoning then. Defeasible reasoning is an area which tries to study this. What types of conclusions can we draw from this? So here's a quote from Douglas Adams, who years ago in one of his Hitchhiker books had made the wonderful statement, "We demand rigidly defined areas of doubt and uncertainty." because this is precisely what we have, right? We have some fuzzy or feasible soft information, but we want to know how to deal with them. We want really formalized ways to be able to deal with them. So this is an ongoing area of research. As I've just shown you, there are different modes of defeasible reasoning. And the interesting thing is that in many cases, they can be reduced to set solving. What I mean by that is there are ways to recompile this defeasible reasoning into classical reasoning. It's in some sense, it's like putting a wrapper around it. And the nice thing about this from a computational point of view is that means that if you have a really good SAT solver, then you can suddenly do defeasible reasoning as well if you just do a little bit of extra work before you start. So far I've gone on about SAT solving and the fact that SAT solving can be really efficient. SAT solving is associated with Boolean or propositional logic. But it turns out that, well, two things. In many cases, we want to go beyond propositional or Boolean logic to look at logics or languages that can give us more than just what these classical logics can give us. And I'm not going to go into details. This is an example that I'm not going to go into detail as well, but the point of the example is that what I have here in natural language cannot be expressed in Boolean logic. It can be expressed in something called a description logic, or in first order logic. My guess is that while many of you would have probably heard of first order logic or predicate logic, you may not have heard about description logic. The point here is that we can go beyond Boolean or propositional logic. Firstly, to be able to define what it means to draw these conclusions. And also there are tools for reasoning with these extended logics as well. So we can go beyond the Boolean or propositional case. Right, this then finally brings me to what the title of my talk promised, and that is CAIR in the age of machine learning. So I want to talk a little bit about the link between knowledge representation and machine learning. I want to start off by the following three statements, which I think is not controversial. The first one is, well, looking at the name itself, machine learning is good or aims to be good at learning, right? So the focus there is on learning. CAIR, as I mentioned a little earlier, is not so much concerned with learning. That's not to say that none of the work in CAIR has anything to do with learning, but in a big part of the CAIR community, the assumption has always been, we'll have someone that will give us the knowledge. And once we have the knowledge, then we can do interesting things with it. We can do intelligent things with it. We can reason with it. So CAIR is good at drawing conclusions. Many ML tools tend to be a little bit opaque, right? The term black box has been used. If you draw a conclusion, let's say you apply for a home loan and there's an ML tool that tells you, or that tells the bank that the home loan should not be allocated to you. And if you ask why, well, then the answer is, you know, the machine said so. The computer told us that you're not eligible, but there isn't necessarily a nice explanation for why this is the case. Whereas on the other hand, CAIR tools tend to be really transparent. The whole idea is to be very declarative and write the information out, you know, that I've shown you by, you know, the information about birds being able to fly or not, and so on. And it then turns out that by its very nature and by the way in which the conclusions are drawn, CAIR tools are transparent. So if you were to ask, you know, why is it the case that penguins don't fly or robins don't fly, or whatever the case might be, I can trace it back to the explicit information that I have in there, and I can give you a nice coherent explanation that a human can understand. So in that sense, CAIR and ML are complementary. So what I want to do is I want to give you on the next 2 or 3 slides, a nice example, one case of how CAIR tools and ML tools can be combined to produce something that may be kind of more than the sum of the parts. It turns out that some, but not all, machine learning classifiers can be compiled into Boolean formulas. So what do I mean by a Boolean formula? Well, it's the stuff that I showed you a little bit earlier about P and Q and so on. It's also the case that Boolean formulas can be compiled into something called Boolean circuits. It's really just a kind of a compressed version of a Boolean formula, if you like. And Boolean circuits can be used for explanation. So what I have on the slide here on the right is a Boolean formula that was compiled into something that's called an OBDD, an ordered binary decision diagram. So think of these, the nodes that I have over here as Boolean variables. They can be either true or false. And if there's a dotted line going out of a Boolean variable, then that indicates the case where the Boolean variable is false. If there's a solid line, it indicates where the Boolean variable is true. So this is a little Boolean formula, an OBDD, that can help you decide whether somebody should be admitted to university. Now, the argument here is that this type of thing can be constructed from an ML classifier. You can use lots of data, and then you can use these as your as the attributes, and then you come up with a formula like this. Okay, so how can this be used for explanation? Well, let's look at an example. Suppose I have a student or a potential student, and I know that the student passed the entrance exam, that they're a first-time applicant, that they have no work experience, and that they have a high GPA, grade point average. Then you can see that they would be submitted, that they would be admitted, right? So they passed the exam, they're a first-time applicant, they have no work experience, and they have a high GPA, so then they're admitted. So far, so good. It's just a way of drawing a conclusion, nothing more. But I can give you a reason for why the student was admitted. And the reason is that it's because they passed the entrance exam and that they have a high GPA. So what I'm saying is, from this, you can extract the fact that even if they had other variables or other values for the other two Boolean variables that they had here, they would still have been admitted. So that's a very nice version of an explanation. It tells you it gives you the essence of why the student was admitted. I can take this a little further. So let's extend this Boolean formula and add another one, another Boolean variable called rich hometown. And the moment you see rich hometown, you should already know where I'm heading with this. We want to be able to pick up bias in some sense, right? So suppose I have a student, and I know the student passed the entrance exam, they're a first-time applicant, they don't have work experience, they have a high GPA, and they're also from a rich hometown. Then firstly, I can again, if I look at the reason for admission, and I'm not going to go through the details, but it's relatively easy to do so. I can show you that the reason for admission has nothing to do with them coming from a rich hometown. It's because they passed the entrance exam and because they have a high GPA. On the other hand, I can now do, because I have this information, I can do a version of counterfactual reasoning. In other words, reasoning about what would have been the case if something had been different. I can show that this student would have been admitted even without a high GPA because they are from a rich hometown. Okay, so now there's a notion of bias coming, right? Now, the point over here is that this information could have been constructed from an ML tool, but it's because it's been made declarative in this way that you can perform this type of reasoning. And more generally, what we can do is we can use this type of reasoning to identify bias. In other words, we can make, sometimes we can identify biased decisions. Something is biased because some Boolean variables are protected. Right? So in this case, the admission decision will differ for two candidates who differ just on rich hometown. Now, let me be clear, bias is not necessarily a bad, right? So if you're interested in getting the best students, then maybe the entrance exam, maybe the decision to admit someone should be biased against, or biased in terms of the entrance exam. But the important thing is, sometimes there are biases that creep in that we don't know about. So when we do this, when we have this type of tool available, what we can do is we can identify the biases, and then we as humans can sit and decide which of these biases are acceptable and which are not. Whereas if you don't have an explanatory mechanism, you're stuck. The decisions are being made and it's not quite clear why they are being made. So my point about all of this is that what we have here is an example, a simple example, but an example of how you can use the usefulness and the power of machine learning tools and combine that with CAIR tools to get something that's really better. Okay, so to summarize in some sense, and this is my kind of take-home message, if you like, about CAIR in the age of machine learning, and that is that as ChatGPT already indicated a little bit earlier on the slide, these are not competing mechanisms within artificial intelligence. They are complementary. And the idea is to combine them to create better tools, and not so much whether you should use one or the other. So here's a nice quote by Stuart Russel. Stuart being, well, he's famous for many things, but one of this is that he, between him and Peter Norvig, they wrote the most successful AI textbook in the world. It's been the standard textbook for years. So Stuart says, I would say that language understanding, at least in a simplified sense, so that particular aspect of intelligence will become possible in this decade. And I think it'll be a combination of deep learning with probabilistic programming with Bayesian and symbolic methods. Symbolic methods being the logic-based stuff, in other words, being CAIR. Okay, so this brings me back to the question of, can machines think? You know, I started talking about knowledge representation and machine learning after that. And you may remember that I said that Jerome Wiesner, who's the special assistant to the US president for science and technology, says that I suspect that if we come back in 4 to 5 years, I'll say sure that machines really do think. Okay, so let me show you a little video of Jerome, and I'm hoping that this will work.
With me tonight,
So for those of you who couldn't quite hear what Jerome was saying, he was saying, okay, it's going to happen in 4 to 5 years. But the point is that he said this in 1960. So he was the advisor to the US president at that point. And the reason I bring this up is because it seems to me that every 5 to 10 years, if there's some kind of breakthrough in AI, there's a question, can machines really think? And then many people say, well, you know, give us another 5 years or so, and then maybe they can. So maybe we should stop worrying about whether or not machines can think, and just realize that they can, the intelligence that we've built into machines can be really beneficial. And in that, I really like the quote by Edgar Dijkstra, who is one of the more controversial computer scientists. He's also been around for a while. And as you can see there, he makes the following very valid point in my opinion, and that is the question of whether machines can think is about as relevant as the question of whether submarines can swim. It's the wrong question to ask. So I think that is the last slide that I have. Oh, yeah, I've right at the end, I added 2 more slides because I recently became aware of something called Whisper. I don't know how much of you know about Whisper. So Whisper is a tool that was developed by OpenAI, and it's a speech-to-text transcriber. So the nice thing about Whisper is that OpenAI made it available. It's openly available for anyone. And then some guy recently, Gerganov, some Bulgarian guy, apparently, went and wrote a C++ implementation of this. So what you can do now is you can download his C++ implementation. If you're a coder at all, you can download it. It's apparently 10,000 lines of code, so you can easily run it on your machine. And I haven't tried it, but apparently it works fantastic as a transcription tool. When there's dictation and so on, it transcribes really, really well. And this is the way I think we ought to think about these AI tools. They are incredibly useful for helping us as humans to do things, and we should stop worrying about whether they can think or not and just get on with getting them to help us to do what we want. Okay, I think I'm going to stop there. So thank you very much for your time and attention. And I think we're going to have a Q&A now, right?